NATO operates one of the largest collections of combat aircraft on Earth, but the aircraft are not equal. Across 32 member nations, you have jets designed before color television was standard, still flying alongside aircraft that their designers could not have imagined. The performance gap between the best and worst NATO jet is not a minor engineering difference. It is an entirely different era of warfare, operating under the same alliance flag. If a real high-end air war started tonight, not a patrol, not a low-intensity operation, a genuine peer engagement, some of these jets would dominate from the first minute. Others would not survive their first engagement. The reason is not pilot skill. Pilot quality across NATO is a constant. The reason is physics. And physics does not negotiate. Modern air combat is decided before pilots ever see each other. Detection, tracking, missile reach, survivability, lose that exchange, and the fight is already over. The missile is already in the air. So the question is not which jet looks the most capable on a flight line. The question is which one survives long enough to matter. Today we rank the major NATO combat jets by how they would actually perform in a real conflict. Using 6 weighted criteria, verified engineering data, and honest trade-off analysis. No hype, no fan scoring, just the hardware. Every aircraft in this ranking is scored across 6 weighted categories, not opinions, not reputation, not how the aircraft performs at an airshow, measured verifiable performance data. Here is why the weights matter. Because this is not obvious. If all 6 criteria counted equally, you would get the wrong answer. A fast but fully detectable aircraft and a slow but nearly undetectable one are not equivalent threats. One gets shot down before it fires. The weighting reflects how modern air combat actually works, not how it worked in 1970. Category 1, Survivability and Stealth, 25%, the highest single weight. Because if the aircraft does not survive first contact, the other 5 criteria never get tested. Category 2, Sensors and Avionics, 20%. Radar type, data fusion, situational awareness. Seeing first is functionally the same as shooting first. Category 3, BVR capability, beyond visual range, 20%. Missile integration and effective engagement reach. Modern fights are decided here before either pilot has visual on the other. Category 4, Payload and mission flexibility, 15%. What the aircraft carries and how many missions it can perform. Category 5, Kinematic performance, speed, altitude, energy retention, 10%. Still relevant. No longer the deciding factor it once was. Category 6, Cost effectiveness, 10%. A platform that cannot be sustained at scale is not a strategic asset. It is a constraint on the alliance. Same rubric, same weights. Every aircraft. Let us start at the bottom. Starting at the bottom. The F-4 Phantom II. Greece is the only NATO operator still flying it in meaningful numbers. And here is the data point that tells the whole story. The Phantom's core radar technology is approaching 60 years old. In 1958, that radar was a genuine military breakthrough. Against a modern AESA-equipped adversary, it is a sensor liability. Fast on paper, blind where it matters. The threat is detected, tracked, and engaged before the Phantom's own sensors resolve the contact. Survivability is the first criterion. The F-4 fails it at the system level. It ranks last. The Panavia Tornado, a machine engineered around one very specific problem: penetrating Soviet-era air defenses at ultra-low altitude. Variable sweep wings, geometry that physically changes in flight, optimized for treetop-level speed above everything else. For that mission, it was exceptional. Here's the problem: that mission no longer defines modern air combat. Mechanical radar, No viable AESA upgrade path, no stealth geometry. The threat environment it was built to defeat has evolved. The aircraft has not. It is not a poor design. It is a precise design, built for a different war. One aircraft always comes up. The A-10 Thunderbolt II. It is not ranked here, because it is not a fighter. Mach 0.720 BVR capability. Outstanding close air support platform. Completely different mission category. Exceptional at what it does. What it does is not this fight. The original F/A-18 Hornet, still in limited NATO Allied service, a genuinely capable multi-role platform, carrier-capable, dual-role, economical to sustain. For a smaller Air Force managing diverse requirements on a constrained budget, it is a rational procurement choice, but range is a hard number. The legacy Hornet's combat radius, approximately 330 nautical miles, is the shortest of any frontline NATO combat jet. In a large-scale conflict, distance becomes a weapon. A jet that cannot reach the target cannot affect the outcome, regardless of what it carries. The Hornet performs well inside its radius. Outside it, the geometry simply does not work. That ceiling is not political, it is physics. The F-16 Fighting Falcon, older block variants, the A, C, and D models, the most widely operated fighter in NATO. Over 800 examples estimated across the alliance. Lightweight, agile, an elegant aerodynamic solution to the 1970s air superiority problem. But modern air combat has moved away from that problem entirely. Close-range turning performance matters less when engagements are decided at 40 miles. Older F-16 blocks rely on mechanical radar, which means an adversary's AESA system is actively tracking the aircraft before the F-16 has resolved the threat contact. Single engine over hostile territory adds a second operational risk that cannot be upgraded away. Still dangerous, at a structural disadvantage in a high-end fight. That is the lower tier. Capable platforms in the right context. But against a peer adversary with modern sensors, mechanical radar, and limited survivability are structural disadvantages from the moment you enter contested airspace. Now, the aircraft that actually shape outcomes. Number 5. The F-16 Block 70 and 72. Called the Viper by the pilots who fly it. Here's what most people miss about this aircraft. The APG-83 ADSA radar fitted to the Block 70 uses technology derived directly from the F-22 Raptor program, not an approximation of F-22 sensor capability, a direct technology insertion into a 1974 airframe. That is the Viper's story. A design that first flew 50 years ago now carries one of the most capable radars in the NATO inventory. Conformal fuel tanks extend range without external drag penalty. A modernized electronic warfare suite closes the survivability gap significantly. Its decisive edge is cost-to-capability ratio. For any NATO ally operating under real procurement constraints, which describes most of them, the Viper delivers near 4th generation plus performance at a fraction of the cost of an entirely new airframe. In any serious defense budget conversation, that matters enormously. The limiting factor is physics. The core aerodynamic design is 50 years old. Certain performance ceilings are fixed. Single-engine configuration over hostile territory remains a material operational risk. The Viper proves a legacy airframe can still compete in the modern environment. It does not prove it can lead in one. Number 4. The F/A-18E Super Hornet. Make no mistake, this is not an upgraded legacy Hornet. It is a different aircraft sharing the same family name. Larger fuselage. twin GE 414 engines. Combat radius extended beyond 400 nautical miles, a meaningful operational improvement over its predecessor. The ANAPG-79 AESA radar, full AIM-120D AMRAAM integration, nearly 18,000 pounds of payload capacity. By pure capability numbers, it is a serious multi-role platform. Its decisive edge is carrier operability. The Super Hornet sustains U.S. Navy carrier air wings, a form of distributed power projection that no other NATO ally replicates at scale. That is not a hardware advantage. It is a strategic architecture advantage. The limiting factor is aerodynamic drag. The Super Hornet's airframe geometry generates significant parasitic drag at high speed, costing velocity and fuel efficiency in any sustained high-energy engagement. Not a fatal flaw, but a real one that the data confirms. Number 3. The Eurofighter Typhoon. Operated by the United Kingdom, Germany, Spain, and Italy. Built by 4 nations with one primary objective: air superiority. And in one specific performance domain, it achieves something no other NATO jet in this ranking matches: instantaneous turn rate. At 65,000 feet service ceiling and Mach 2. The Typhoon is already competitive across kinematic criteria. But it is the angular rate, the speed at which it changes nose direction, that makes it exceptional at close range. In a within-visual range engagement, the Typhoon is the most dangerous platform in this ranking. The Captor EAESA radar, fitted to current production variants, brings the sensor suite fully into the modern tier. Decisive edge, within visual range dominance and kinematic ceiling. The limiting factor is honest and important. Compared to the Rafale and American platforms, the Typhoon has accumulated less combat validation data against peer-level adversaries. Its performance in a genuine high-end engagement remains an open empirical question. That is not a criticism of the design. It is a data gap. Exceptional on current evidence. Untested at the highest level. Number 2. The Dassault Rafale. The reason it ranks second is not any single exceptional system, it is how the systems work together. Most NATO fighters are capable platforms with capable radars and capable weapons. The Rafale is a unified combat system, where radar, electronic warfare, weapons, and data link share a common architecture. That is a design philosophy, not a feature list. The RBE-2 AESA radar. The Spectra electronic warfare suite, one of the most operationally capable jamming systems currently fielded on a frontline NATO aircraft. And Meteor missile integration. The Meteor's no-escape zone, the envelope from which a target cannot kinematically exit, is substantially larger than the AIM-120D AMRAAM carried by most other NATO aircraft. In a BVR-dominant engagement, that reach advantage is measurable and real. Decisive edge, system integration depth. Combined with the most capable long-range missile currently in NATO service. Limiting factor, approximately 100 operational airframes. In a sustained high-tempo conflict requiring high sortie rates, that is a constrained resource pool. A complete aircraft, a limited one. Number 1. The F-35A Lightning II. Before we get into why, let us be honest about what it is not. The F-35 is not the fastest aircraft in this ranking. The Typhoon is faster. The Viper is faster. On raw top speed, the F-35 sits last among the top 5. It is not the highest flying. The Typhoon reaches 65,000 feet. The F-35 does not match it. And in a sustained turning engagement against a Typhoon or Rafale, the F-35 loses. The engineers who designed it knew that. They designed it that way. So why does it rank first? Because in this rubric, with survivability weighted at 25% and sensors at 20%, the F-35 leads in the 2 categories that matter most in modern air combat. Its radar cross-section is orders of magnitude smaller than any conventional fighter here. The F-35 typically reaches effective weapons range before it appears on the threat radar. It shoots first, not occasionally, as a consistent function of its design. The APG-81A radar combined with sensor fusion allows it to simultaneously track and engage multiple targets while broadcasting that picture to every networked aircraft and asset in range. It does not just fight, it organizes the fight around it. Decisive edge, first shot advantage, structural, not circumstantial. Limiting factor, kinematic performance. In any scenario where stealth fails to prevent detection, it is aerodynamically outmatched. The F-35 does not try to win a turning fight. It tries to prevent one from happening. One aircraft is not included in this ranking. The F-22 Raptor. It is operated exclusively by the United States Air Force. No NATO ally flies it. No export variant has ever been approved. Mach 25 Super Cruise sustained supersonic flight without afterburner. Ceiling above 65,000 feet. Combined aperture avionics, thrust vector control. By any measurable criterion, the most capable air superiority platform ever produced, but it is not part of the shared NATO inventory. It belongs in a separate benchmark category, and that is precisely where it stays. Behind every ranking number is a pilot whose life depends on which side of it they're on. Not in a statistical sense, in a specific, personal, irreversible sense. That is why this channel exists. Not to win arguments, not to promote any nation's aircraft or any manufacturer's product. To understand what the engineering data actually says, because the pilots flying these machines deserve that level of clarity. If you disagree with the ranking, good. That means you are thinking about the trade-offs. Tell me exactly where the model breaks. Leave it in the comments. Hardware of peace, no hype, just hardware. Subscribe. Next, hypersonic weapons, and why no nation has yet solved the problem of stopping them.